Thank you very much, Pietro. And thank you everyone for coming. I'm very excited to give this talk. This is some of the work that I've been doing. It started actually, this project, the idea of optimizing crutch designs, started with the engineering design team in Cambridge already a few years ago. And I jumped on this project about a year and a half ago. And then I was able to bring it on more recently with the help of the computer science department through Bayesian optimization. So let's go through it. Perfect. Okay. There is a challenge when it comes to crutching, and that is that for the last 100 years, the crutch designs that we have basically haven't really changed, and they are used by about 200,000 people in the UK alone. And as you can see, and across a variety of population, the population that uses them is quite heterogeneous. It includes both young people because of ankle sprains, as is shown on this right-hand side, as well as older people, or sort of from 60, 70, 80 plus, because of ankle fractures. But also the indications are basically any sort of lower limb injury that requires rehabilitation. Now, the challenge is that these crutches not only haven't changed, really, but cause issues just as much as they help things. So, for example, the historical auxiliary design shown here on the sort of top left corner has well noted evidence of palsy, in other words, a compression of the nerves underneath the armpits. This is one of the reasons why it's less used in the UK and Europe in compared to the US. But it's not like the elbow crutch, which is the alternative, is necessarily that much better, because by its very geometry, it forces a lot of load to be on the wrists, as well as the forearm, but specifically on the wrist, causing itself a set of nerve palsies around that area. Now, in the last sort of 20 years, there have been a variety of studies that have tried to understand crutching dynamics to try to improve on the current crutches. As you can see, this table, this is an excellent survey which looks at the kind of data that is analyzed to try to make sense of these crutching dynamics. But all of these studies have one thing in common, that they are trying to find a design that is ultimately sort of the optimal one for everyone. And that is inherently going to be an issue. Well, instead, what we need to look for, what we need to try and find is how to rapidly personalize the geometry to each individual who needs it. And this is the aim of the project. So how can we do that? So first of all, you can break down a design of a crutch into three main parameters. Your angle beta, which is the angle from the horizontal arm grip to the diagonal forearm placement. This is the angle beta. The angle alpha, which is instead is the angle from vertical of this horizontal arm grip, hand grip. And then the distance gamma, which is the distance from the forearm placement to the vertical strut. In this way, you can describe any elbow crutch. This is, and as we can see on the top left diagram. Now, through the help of Christoph Schiening at the physiology department, we were able to build a flexible design, as you can see on the far bottom left figure, that allows us to explore these three parameters nearly fully. We were able to nearly reach all the potential combinations of these parameters with this flexible design. But this is still useless unless we put it in the context of the model that will allow us to discover this personalized geometry. So how can we do that? One way is through Bayesian optimization. One of the benefits of Bayesian optimization is that through Gaussian processes, is that it is a way to rapidly find the optimum of an unknown function that cannot be that you cannot simply run a gradient descent on. In some situations, it's used, for example, to tune most effectively the hyperparameters to a neural network. So rather than in grid search, you are combining this idea of exploring the space of the hyperparameter and exploiting what you already know is good. And it does that by being probabilistic. And it's excellent when it comes to dealing with real world challenges, such as crutching. It's excellent because the probability is required to deal with the noisiness of the data. The humans are noisy, the crutching is noisy, and yet, despite that, it's still able to both explore new geometries and take into account what are the best geometries that it's looked at so far. So, with that in mind, let's run through this experimental loop. We start with initial crutch design. We've started for this one with the NHS, standard NHS crutch. This is what we want to improve on. We run our first experiment. In other words, we crutch, and the experiments are done indoors at the moment with one user, that was myself, over a sort of 15-meter corridor, and you go up and down about 6 times. This is a total of around 90 steps, straight line. It's a simple start to this challenge. From that run, we start to collect some metrics. Now, the metrics are collected by having the user put on a H10 heart rate accelerometer. This acts both to detect the heart rate as an ECG, and it has an accelerometer inside of it, which allows you to detect steps and acceleration as it goes through the crutching. And we'll look at that next. We extract, once we finish the crutching, we extract the metrics and we combine them into a loss, which we then give to our Gaussian process and say, well, now that you've seen what this specific geometry is, give us what you think is going to be the next best geometry. This is what the model gives us. We input this model into a simulator of a flexible design to make sure that indeed it is a viable geometry, and then we run the experiment again. Through this experimental loop, we can ask 2 questions. The first question is, can we indeed use Bayesian optimization to rapidly discover an optimal crutch design for an individual? We don't want to do 10 experiments for one person or go across the full parameter space, but it's also unlikely that we're able to do a zero-shot prediction, given that it's very hard to simulate this kind of noisy system in the first place. So can we use Bayesian optimization to rapidly discover a better crutch geometry that is tailored? And second, one of the beauties of using Gaussian process is the fact that you can then query the knowledge that it has gained from this data to better understand crutching dynamics. And as we'll see right at the end, the beauty of this system is that once it can do it for one person, it can more rapidly do it for another. And that is the beauty of this Bayesian optimization, the Gaussian process. It can rapidly transfer, but we'll look at that later. Okay, so with that as a workflow, let's look at the metrics. So in the top left, we can see a depiction of the accelerometer. It is a little device that sits right in the middle of the chest on the heart rate monitor band, where the X acceleration is downwards, the Z acceleration is the tilt, and the Y acceleration is the lateral motion, it's the lateral acceleration. This is this accelerometer doesn't have a gyroscope in it, which means that as you twist the accelerometer, it will be the X, Y, Z acceleration vectors and are combined as opposed to maintaining their specific directions. This is quite helpful when trying to do the first step of collecting a metrics, which is to identify the steps. If you combine the X and Z, and this is the downwards and the forwards, by taking their absolute terms and combining them and adding them together, you end up getting this very repetitive accelerometer trace, which we do for this kind of crutching, the three-point crutching, which we're looking at, which is made up of the landing of the person, a switch, a sort of moving of the weight forward, followed by a placement of the crutch, which is right in the middle. Then the swing of the body through the crutch until it lands again. This is one step. Now, from this step, we can start to discover some or extract some metrics. And the metrics that we want to extract need to follow three main themes: instability, effort, and pain. These are the things that we want to optimize. And so the metrics need to extract them, and then these all come into one loss that we end up trying to optimize. So what's interesting about this method as well is that we want to both combine the subjective and the objective measures. This is because ultimately a crutch isn't just good if an accelerometer says it is good, but if ultimately you say if it is good. And joint pain is a subjective measure, so is instability, and so is effort. So the loss is this combination of both the subjective measures and the objective measures. So the objective ones are the change in the X and Z acceleration data. And this change is looking at the first two, what we call bout. A bout is one of these 15 steps. So we're doing 6 of these. So if you take the X and Z acceleration for the first two and the last two, and you take that difference, then that is one of the metrics. That's what this one, delta X plus Z. The idea behind that is that if you're crutching energetically, the X plus Z is going to be, acceleration is going to be quite high. And if you start to feel fatigue or instability, you're going to gradually slow down. Your energy, the energy you're putting in the crutching isn't going to be able to be maintained. So we want this change to be as low as possible. The delta Y is, again, similar to delta X plus Z. It's looking at the Y acceleration in the last two bouts of crutching versus the first two. Now, this delta Y is even more specific to instability because it is specifically looking at the lateral motion. So as you're crutching well, you're not going to have much lateral motion. The moment you start to be unstable, it's going to increase. A good crutch isn't going to change as you do your 90 steps. So we want this difference to be minimized. But obviously, if the crutch is already so unstable that you are hardly moving from the get-go, then sure, this difference, this delta Y between across the bouts is not going to be very high because you're not changing the way that you're crutching, but still it is unstable. And this is why we add a sum, an absolute Y acceleration. And then finally, we add the change in heart rate from the start of the crutching period to the end, the average step frequency for each bout, and the step frequency standard deviation. So again, if you are crutching well, as you are stepping through, you're not going to have much change over the frequency. But if suddenly you, again, take a misstep, that's going to be shown up in this loss. So we take all of these and put them as a combined subjective and objective loss. Now, the next thing we're going to do is define the model. The model that we use is a Gaussian process with a Matern kernel 5.2 with a white kernel for the beta parameter. Now, the beauty again of having a Gaussian process is that we can input a prior belief of this loss function in the kernel. Obviously, as the data comes around, this belief is going to be updated by the data in a Bayesian way. But the choice that of having a 5.2 is to say that yes, the crutches are going to be relatively similar to each other, but at some point, they're not, the loss between them isn't necessarily going to be smooth. In fact, it's going to be similar, but it can jump across. And this is very typical in natural environments. Second, the white kernel for the beta parameter. The beta parameter, if you remember, is the angle between the forearm placement and the arm placement. And what's the reason why we added this beta parameter, sorry, this white kernel noise, in other words, this noise around the specific parameter, is that it's actually quite difficult to be very precise on where one places your hands when you're crutching, especially when on the flexible design that we created. We also set up a length scale of 3, and this was again based on this assumption that the correlation across 2 neighboring geometries would be around 50% correlated. And we used an expected improvement function for the Bayesian optimization loop, as it's slightly more exploitative as opposed to explorative, and that helps to decrease the number of goes that we need to have to find the optimal crutch. We don't want to explore the full parameter space. We want to get to the optimum as quickly as we can. Okay, so let's have a look at some results. So this is one of the various Bayesian optimization loops that we ran. And we start the user with 3 initial points: the NHS crutch, a smart crutch, which is one of the alternatives on the market, and the Opmo crutch. Now, Opmo is the name of the project run by the engineering design team at Cambridge, and their crutch was the best that we ran here, was the best that they had come up with before I entered the team and the project. So we start off with these 3 runs, and this combined loss is this combination of the subjective and objective loss on the right. Now, the B0B01 is that first Bayesian optimization suggestion. As you can see, the loss increases. It is exploring. But already by B02, by the second suggestion, the loss has decreased by about 40–50% compared to any of the other previous best crutches that we had. And this is both in the subjective and especially in the objective ones. And now what's interesting about B03 is that, as you can see, it's basically saying, give me the best, or give me the same 2 parameters of B02, but let's change one of them. Let's change the third gamma just to see what happens then. In other words, it is rapidly discovering a better crutch, and it is exploring the space as efficiently as it can. Now, if we stopped at this point because, again, we don't want to be running multiple experiments for one person to discover a crutch, even if that person is the first one. In this case, this is the case. Okay. So far, we've shown that, yes, indeed, we can use a Bayesian optimization loop to rapidly discover a better crutch design. But the second question that we had was, can we use the Gaussian process and the data that we have to understand better the crutching dynamics? So this table is a simple correlation table of the various metrics across as they change and their correlations with the three parameters. Now, the first thing that's worth saying is that alpha, which, as we recall, is the angle of the horizontal arm rod compared to vertical. So in an inch crutch, this would be 90, and then it can be either higher, in other words, over 100, or lower, around 70. And this, we're varying it between 70 and 100. This is the one here. Alpha is it's pretty strongly correlated with subjective effort. And subjective effort has an 82 percent correlation with the overall loss. In other words, if you were to simply ask someone how effortful is this crutching, that is pretty well correlated with the instability, the effort, and the pain. In other words, and so this is already sort of suggesting that alpha is a pretty important parameter to optimize this crutch. The next one that I think is worth talking about is beta. This is negatively correlated with subjective joint pain, and positively with instability and heart rate change. Now, the joint pain is interesting because, again, beta is this angle here. In other words, when beta is larger, the joint pain is smaller. This makes sense because as you are crutching, if beta is around 90, you're basically if alpha is also around 90, all of your weight is going on your wrist. The moment that beta increases, it doesn't really, that means that regardless of what alpha is doing, the weight shifts and is distributed better across both the wrist and the forearm. And so the larger the beta, the lower the pain. And the last one, gamma, is also quite interesting. It's quite strongly correlated with total step frequency variation, the step frequency, and the XZ change. And this diagram on the right goes to explain that. So gamma is this distance here between the yellow, for example, and this joint, and the red and the joint. So gamma in the yellow is 0, and gamma in the red, let's say, is about 10 to 20 centimeters. Now, as gamma increases, it's going to be more correlated with a step frequency variation and XZ change. So in other words, when it's and the way to think about it is to interpret these results is that when gamma is 0, the rotational moment that is happening, here we go. The rotational moment that occurs when someone is in the middle of the swing is as big as it can get. In other words, it's as if you're dropping a ball on a hill, and it's always going to go down exactly the same way. It doesn't matter how you place the crutch, you will be pushed forward in a way that in some ways decreases that variability. But it's also, it feels when you crutch on something like this, as if you're planting and dropping and falling forwards. Instead, as gamma goes closer to the hinge point, then you have less of this sort of plant and fall. It's a smoother crutching motion, but it's also going to be more variable. We can keep talking about this, but the next bit of analysis that we can do is sensitivity analysis. Now this, instead of querying the data, is querying the model. This is querying what has the Gaussian process learned across so the first three are the first order indices, Sobel indices. The next three are the second order indices, and the last three are the total order indices. In other words, the way to interpret this is what variation in the output is explained by the variation in the input. In other words, as alpha changes, how does any of these specific metrics, interpretable metrics, also change? Now, what's especially interesting is these very high numbers. The beta seems to explain the whole of subjective instability, basically, as well as the whole of Y change. This is interesting, again, because it's not an expected finding. Beta is, just to recap, is the angle between the forearm and the handle. And there is no, and the way that these numbers are sort of come about is that they sort of say they run through all the possible simulation, all the possible variety of data. In other words, when beta, as you know, regardless of whether beta is large or small, in relation to both alpha and gamma changing. Now, this is an interesting finding. It is against our expectation, and there is no, at least that I have thought of, clear way to make sense of it. And this is one of the potential limitations of this work, but also something that gives a lot of food for thought. Okay, and the last thing that we can do again to query the model is to ask it to predict across this parameter space, where does it think the best crutches are, and where does it think, you know, and how confident is it about that? So over here, we have these three cubes, and these cubes are made up of the parameters, the alpha, beta, gamma parameters that make up the crutching parameter space. This empty sort of cropped area is the geometries that are physically possible. Each point here, each big circle, is an experimental run. And it's colored by the loss, this combined loss that we created. The brown circle is, given these 13 runs, what is the net, what does this Bayesian optimization loop suggest? So in other words, this is the one that it thinks has the lowest, is going to have the lowest loss and the lowest uncertainty over it. Now, one thing that I've sort of skirted over until now is this choice of length scale. As I mentioned previously, we picked as a prior a length scale of 3, motivated by the fact that two neighboring geometries should have around 50% correlation. This is actually quite difficult to test. And what we can see, these two plots are the prediction, the uncertainty across different length scales, the length scale of 25 and 15. And as you can see, obviously, because this is a sort of 1,000 large parameter space, and we've only got 13 data points, the moment you start to decrease the length scale, the less it wants to say about anything that's further away from it. Now, one of the things that could be interesting to test is what is the impact on the BO loop as we increase the length scale, and as we basically start to say that these crutches, even though they seem quite far away, they are relatively similar to each other. And this is an open question. Okay, last slide. There are some limitations, obviously, to this work. First of all, it's only done on one person so far. We haven't repeated the Bayesian optimization loop across various length scales and variance for the Matern 52. And ultimately, even for one person, if you were to ask them to repeat the same crutch, the same geometry, they would probably have a variation in the loss. There's a noise to the loss. And we didn't explicitly model this. In fact, we sort of assumed that this noise would be very minimal. but actually can be quantified, it should be quantified. And but in small data settings, that makes it very difficult for the GP to learn. This actually leads quite nicely into future work, where the central point of future work is to think about transfer. Transfer obviously is a challenge both from a it's challenging to prove that it works in some ways, but there are ways to do it. And secondly, what you're transferring isn't just needs to be careful about what you pick, because the objective metrics might be able to transfer well, but the subjective ones probably don't. And so maybe you might need two different GPs, one for the subjective, one for the objective, or potentially just to skip the subjective and transfer only with the objective metrics. Now, and finally, one of the things that we want to improve on is that the flexible design that we have at the moment still cannot reach the full parameter space. In fact, that final Bayesian optimization suggestion is something that we couldn't physically run on our geometries. So that's it. Thank you very much for listening to me and coming to the talk. Many thanks to Christoph Schwiening, Ian Hosking, Carl-Henry Eck, and all of my collaborators on this project. Let me know if you have any questions, then please ask.